Hello everyone. I'm Trần Quang Duy from Group 5, and today I will have a presentation about input output, also called I/O in computer architecture. So so the first part is Nguyễn Duy Bách will take the question number 1, 2, 3, and 4.
Hello everyone, my name is Nguyễn Duy Bách, and my part is to brief revisions about question 1, 2, 3, and 4. The questions 1 is explain the advantage and disadvantage of different I/O and technologies. There are three input-output technologies, that is program I/O, or we can say Boolean. The advantage is that it's simple to implement, offers fine control over the device, but the disadvantage that CPU is busy waiting and waste on checking device readiness. It not effective for frequent or slow device. The second is the interrupt-driven I/O. The advantage is that the CPU can do all the tasks until the device signal ignites attentions more effective than Boolean. But the disadvantage that lies overhead in handling interrupts is more complex to implement. And the last is direct memory access, DMA. The data is transferred directly between device and memory without CPU involvement. It frees up CPU for other tasks, but it complex and hardware and software coordinations. It might lead to both contentions of the competition for memory access. The second question is, does describe the role to interrupt handling in I/O. There are three key. Interrupt handling allowed a device to notify the CPU when it is ready for data transfer or when an error occurs. Instead of continuously checking device status, Boolean, the CPU can execute other instructions when the device triggers an interrupt. The CPU stops its certain task, saves its data, and runs a specified interrupt server routine, or we can say ASR, to handle the I/O event. Once done, it resumes its various tasks, and there are three key benefits. Increase system efficiency, reduce CPU idle time, and the last is enable multitasking and responsive system behavior. The third question is that compare and constrain memory, maple I/O, and isolate I/O. Here is the table to show the between memory maple I/O and isolate I/O. The address space, memory member AO share memory address space with main memory, but in another place, isolate AO use a separate AO device space. The instruction memory mapper AO use standard memory access instructions, but isolate AO use special AO instruction in out. The hardware complexity in memo mapper AO X symbol. It not attracts AO address decoding, but in isolate AO, it is more complex. The request is separate AO address decoding. The speed memory mapper is slower than isolate AO because it's complete with CPU for memory boost, and in isolate AO is dedicated AO boost. The flexibility memory mapper AO is more flexible than isolate AO because it can use memory opt for AO, and in isolate AO request specify AO ops. For example, we have macOS ARM x86 on, but in isolate we have x86 recency system. So the four questions is explain how DMA work and its impact on CPU efficiency. DMA direct memory access. How DMA work? First is CPU initiates DMA transfer. The CPU sets up the DMA controller DMAC by specifying short destination addresses, data site, transfer directions, read or write. And second is DMAC take over. The DMAC requests control of the system boost via boost request signal. The CPU grant control via a boost grant signal and temporarily disconnect from the bus. Direct data transfer. The DMAC transfer data direct between input-output device and memory without CPU intervention. Once done, the DMAC releases the bus and notifies the CPU via an interrupt. That is the end of my presentation.
Hello teacher, my name is Nguyễn Văn Victor and this is my presentation. The question 5 explain how DMA works and its impact on CPU efficiency. The first impact on CPU efficiency is reduce the CPU overhead. The CPU is free to execute all the tasks while DMA handle data transfer. Faster data transfer avoid the need for CPU managed byte transfer. And the third is minimize interrupt. Instead of frequent per byte interrupt, DMA only interrupt one per block transfer, the graphic card and high-speed network interface. come with question 6. List and briefly define 3 techniques for performing input-output. Program input-output. Data exchange between the processor and the input-output module. The processor executes a program that gives it direct control of the input-output operation, including sensing device data, sending a read or write command, and transferring the data. Interrupt-driven input-output. Processor issue input-output command, then go off to do the other thing until the input-output module interrupt the processor to request service when it is ready to exchange data with the processor. Direct memory access. A DMA module controls the exchange of data between main memory and input-output module. The processor sends a request for the transfer of a block of data to the DMA module and is interrupted only after the entire block has been transferred. Come to question 7. When a DMA module takes over a bus and while it retains control of bus, what does the processor do? The first thing is continuing executing internal operation. The CPU can still perform tasks that do not require the system bus, such as AYU computation, instruction decoding, cache access. The second thing is wait in the bus hold stage. When the DMA controller requests the bus, the CPU responds with a bus grant and release the bus. The CPU cannot access RAM or input-output device during this time since the DMA has exclusive control. The third thing is may enter a low power state. Some CPU can enter a low power mode while waiting for DMA to finish, reducing the power consumption. Resume execution after DMA complete. Once the DMA transfer is done, the DMAC sends an interrupt to the CPU. The CPU regains the bus control and continues normal execution. That's the end of my.
So my name is Trần Văn Duy, and now I will take the next part. Is the question 8. So, what is the international reference of alphabet and comparison with ASCII? The 8 international reference alphabet, standardized at ISO IEC, is a 7-bit character encoding system that serves as a foundation for many modern text encoding, include ASCII. It was developed to ensure compatibility in telecommunication and computing system worldwide. So, in the key difference in the future, the IAR have a bit width same as ASCII, so it's 7 bits. The total character is just the same. It's 128 national variants. Is the area has the national variants, but for the ASCII is it don't have. It's a fixed. So for the usage, the IAR is international standard, and the ASCII is US centric, widely adopted. So the next is the role of I/O controller. The one device communication, manage communication between operating system and hardware device. The two, command translation, convert operation system command into device commands, interrupt handling, handle hardware interrupt for assigned communication, buffering and caching, buffers data between fast CPU and slow device, and handle error handling, detect and report hardware error and many attempt recovery. And the last one, device status monitoring, reports device status as ensure the device is functioning correctly. This rows. The final question, the major function of an input-output model. Device communication is interprets signal from device and translates them into forms the system can understand. Data buffering, temporary store data to smooth out speed difference between device and the central processing unit. 3. Error detection and handling, detect transmission errors and may request retransmission. Control and timing, coordinates the timing data exchange to ensure synchronization between device and the CPU. The command decoding is interpret and execute command from the CPU to I/O device. And the last one, the interrupt handling, signal to the CPU when a device requires attention, reducing the need for the constant polling. Right, that's the my or not my part. Next is the review of the problem.
Hello, I am Hồ Dương Quốc Thông, and I handle the two problems in our group. So the first problem is regarding I/O efficiency analysis. The statement of the problem is a processor running at 2 GHz uses program I/O to read from a peripheral device. The I/O transfer takes 500 CPU cycles per byte transfer. How long does it take to transfer 1 kilobyte of data using this method? What would be the CPU time used if interrupt-driven I/O were used, assuming only 100 cycles are needed per interrupt and 10 bytes are transferred per interrupt? Here's the solution to the problem. For a program I/O, you need to calculate the total cycles. Each byte takes 500 cycles, and we transfer 1 kilobyte or 1,224 bytes. So the number of cycles is 1,024 times 500, which is 512,000 cycles. And then we convert the number of cycles into time. The processor runs at 2 GHz, so it runs 2 times 10 to the power of 9 cycles per second. From that, we get the time is 512,000 divided by 2 times 10 to the power of 9. And the result we get is around 256 micro. In interrupt-driven I/O, we also count the number of interrupts and then count the number of cycles. So each interrupt transfer 10 bytes. So the number of interrupt we need is 1024 divided by 10, or 112.4. We run the number of interrupts to we run it up to 103 interrupts. Each interrupt takes 100 cycles, so the number of total cycles is 10,300 cycles. And similarly, we convert that into the time it takes. 10,300 divided by 2 times 10 to the power of 9, we get 5.15 microseconds. So next is the second problem. The second problem is regarding USB throughput comparison. The statement of the second problem is USB 2.0 has a data rate of 480 megabits per second, and while USB 3.1 supports up to 9.7 gigabits per second. In the A part, we need to calculate how many seconds it would take to transfer a 1 gigabyte file using each standard. And in the B part, we need to calculate the factor in which USB 3.1 is faster than USB 2.0 for this transfer. The solution for this problem is as follows. In USB 2.0, the file we need to transfer is 1 gigabyte or 10 gigabits, or 8 gigabits. So the time it takes is 8 times 10 to the power of 9 divided by 480, the number of megabytes, times 10 to the power of 6, and you get around 16.67 seconds. In USB 3.1, we do the same calculation and we get around 0.825 seconds. From that, you can calculate the speed up factor of USB 3.1 compared to USB 2.0. You divide 16.67 divided by 0.825 and get 20.2. And this means that USB 3.1 transfer the 1 gigabyte file 20.2 times faster than the USB 2.0. That's all I want to say. Thank you for watching.